Hello, everybody, and welcome to ILSI North America's Symposium on current status and knowledge gaps of PFAS analytical methodology. It is 10 o'clock Eastern Time, and we will get started. My name is Neil Saab, and I am Senior Program Manager for Food and Chemical Safety at ILSI North America. This is the first session in our virtual symposium on science gaps in risk assessment for PFAS in food. Future sessions will address exposure routes into foods and also toxicity mechanisms. And these sessions are expected later this summer. Before we get going, as people are still joining the webinar, I'll start with a few housekeeping remarks. We have a large number of participants on the webinar, and as such, all participants will be on mute. We are planning for about 20 to 25-minute presentations from each speaker. At the end of each presentation, we will take a few questions. However, we also have built-in time at the end of the session for a joint Q&A session with all the speakers. So you will have two opportunities to ask questions. For asking your questions, we ask that you post questions in the questions tab. If you look on your control panel towards the bottom, there's a tab where you can write your questions. And if you're asking it towards the end of the session in the Q&A with all the speakers, please identify which speaker you're addressing your question to. If you're having any technical issues, please let us know via the chat button. And I also want to highlight that this session is being recorded, and the recordings will be made available to everybody, excuse me, who has registered for the session, and you will receive an email from us in the next few days with a link to view the recording on our YouTube channel. So with that, welcome you again, and I would like to introduce Dr. Wendelin Jones, our Executive Director, for her opening comments.
Great. Thanks, Neil, and thanks to everybody for joining us today in this first session of our symposium on PFAS. With the number of attendees that we have registered, we know that this is a topic of high interest across the sector, and we are very thrilled to have some excellent presenters join us today. So we've got a number of folks who have differing levels of familiarity with ILSI North America. So I wanted to just take a minute and introduce who ILSI North America is. ILSI North America is a nonprofit scientific organization that advances food safety and nutrition science for the benefit of public health. We do not lobby or advocate for specific policy positions. Rather, we work in a tripartite manner, bringing together scientists from industry, government, and academia to collaboratively address those big questions that no one sector can address on its own. And in fact, having had a chance this morning to look at our registration list for this meeting, I can confirm that we have scientists from all of our sectors. ILSI North America is focused on US and Canada, and we have participants from US and Canada who are from industry, academia, and government. On the lower right-hand side of this slide, you'll notice our 2020 GuideStar Platinum Seal of Transparency. We are one of a very small percentage of nonprofit organizations that have earned this distinction, and we're very proud of it. We were able to earn it because we shared not only what our vision is, not only what our mission is, but also we provide clear metrics on how we are working to achieve those metrics. So with that, I know our next slide is talking about the agenda.
Thank you, Wendelin. So this is an overview of the agenda for today. I will not read this because we will cover those as we go through the speakers. But it's also available for you on our website, so you can view it there as well. And I just want to close the opening comments with having Gwendolyn coming back and say a few words before we get going.
Right. Again, thank you to all of you for attending today. Thank you to our presenters. Want to, in particular, encourage everybody to follow us on Twitter, follow us on LinkedIn, and visit our ILSI North America webpage. One of the pitches I will also include is if you go to our ILSI North America webpage, you'll find that we just launched our registration for the ILSI North America 2020 annual meeting. This includes our science symposium on July 22nd and 23rd. So encourage everybody to go there and register. If you have questions or comments or would like to learn more, please feel free to reach out to myself, Gwendolyn Jones, or directly to Neil Saab for input and advice.
Thank you so much, Gwendolyn. So let's just jump right in. We will start with Dr. Keith Forst, Iowa State University. Dr. Keith Forst serves as a director of the Polymer and Food Protection Consortium in the Department of Food Science and Nutrition at Iowa State University. Dr. Forst has worked for several packaging companies prior to joining Iowa State University. Dr. Forst has done extensive work in method development for extractables and packaging materials, and also in novel bio-based packaging materials. He also works extensively in method development for PFAS analysis in packaging materials and novel coating and adhesive solutions. Dr. Forst will speak on screening and quantification workflows for PFAS and food packaging. Dr. Forst, take it away.
Hello, Neil. Can you hear me okay?
Perfectly.
Okay, so I'm going to thank you again, and it's a great honor that to let me give a presentation here at the ILSI group. Hold them in high regard. So today I'm going to do something. I'm going to talk fast and ask that you put any questions you can, and we'll make sure we address them. But we're talking about screening and quantification of PFAS and food packaging, and we're going to focus on that figure in the lower right there, where you see the French fry holder, the tray, the paperboard that is coated, because the with oil there. The idea is we're trying to prevent that oil from getting through that paper. And that's kind of where we've been spending a lot of our time in the PFAS world. Brief introduction, this is my research team as of May 20th. I won't go through the names, but we are all dedicated to one of these research pillars. So each one of us has a team working on, I kind of direct the team, I do. And we direct the research together, but each one of those folks has an area that they're responsible for. And in our research group, that would be regulatory compliance and method development, like PFAS today. In-process monitoring, we do a lot of work with post-consumer recycling, a lot of shelf life extension, and as Neil said earlier, a lot of bio-based feedstock work. And you're going to see a little graphic to your right, and that little graphic to your right kind of tells you to navigate where we are in the presentation. And as I mentioned earlier, I'm gonna try to move as quick as I can and not waste, so we have can hit our time mark. So one quick thing. I know I got a lot of people on here, and I'm sure a lot of you already know what PFAS is, but I'm going to do a quick reminder of our area. And I took this from Thermo Scientific. We do some work with Thermo Scientific. We have their equipment in our lab. And so where is it? It's pretty much everywhere at this point. Now, you know, firefighting foams, airports, groundwater, they found it in just about everywhere on the planet. But we're going to focus on one area, and that's going to be the consumer exposure in packaging. So we're looking at grease-resistant paper, fast food wrappers, and microwave popcorn bags as kind of our markers. I think it's important to point out that in the last several years, there's been a lot of press. You know, any of the major news sources have talked about toxics in packaging, and they're primarily talking about PFAS. There was just one last week again. So, you know, they're everywhere, and you know, now we have to work with them. I want to throw up one slide to quickly talk about the significant dates in PFAS history. So around 1956, Scotchgard is introduced. 1981, there's evidence of birth defects. And I'm going to jump clear ahead to 2018. We started seeing some what we call PFAS-free zero tolerance packaging proposals. Working on some out in California. I have been out there several times to discuss those. 2019, I spent some time out in California as well, working on press release that states cancer-causing PFAS in paper products and packaging. And in 2020, it's not going away. So kind of where are we and what is known? As I mentioned on the earlier slide, long-chain PFAS with the highest historical production rates include PFOS and PFOA. That's in North America, most production and use in North America. But as I mentioned earlier, and I'm going to go through this quickly, it's been detected in South America and around the world, long-range transport. We've seen some of the highest concentrations in the apex predators, polar bears, mink, bald eagle, river otter, and bioaccumulation is an issue, of course. I think this third point is really important, generally speaking, and we're talking in general terms here. Perfluorinated compounds are allowed for food contact packaging. They are regulated not to exceed 0.5 to 1.2% of dry paper and paperboard intended for certain conditions of use. And we'll talk about those conditions of use in a few minutes. And specific regulatory thresholds are within the inventory. So I want you to think about this for a minute. These limits are over 1 million times the PFOA and PFOS concentrations commonly detected in paper and fiber packaging products. So the reality is companies are still coded. We're still using PFAS. We're still using these treatments. We get products in from around the world. We still see them out of products coming out of Central and South America. We can see some pretty high levels or high concentrations. So it's just something to think about. So what's happening in the U.S.? I threw this slide up there. I belong to a group called the Anticipatory Issues Management Group. And this is, some of you, I'm sure I have some folks out there in the virtual world on this call or on this webinar that know what that is. That's a group of brand owners of quick serve restaurants, some of the largest in the world. And they kind of track, what's going on with issues around the world, not just PFAS, but everything from heavy metals to titanium dioxide, all of those things. And these are a couple ones that have really hit the radar. The HR 2827, or the Keep Food Containers Safe from PFAS Act, is currently in process. In California, they're the complete ban of fluorine chemistry in food packaging. And then in Minnesota, another complete ban of fluorine chemistry in food packaging as of January 2021. And then in Washington State signed a complete ban of fluorine chemistry in food packaging in January 1st of 2022. So some of these are in process, some of these are active, some of these are adopted, and some of these are both. And you can kind of see from the map there of kind of where we are, which states are active or in process. But just something to think about. This is a huge issue. It's a huge issue in packaging. We've done a lot of the experts have done work in water, but we're now doing extensive amount of work in the packaging area. Okay, so this is where it gets kind of interesting. Not that it didn't get interesting before, but this is where things get different. Testing for PFAS is not perfect, and results are subject to lab practice and methods. And I want to make this very clear to everyone on the meeting. This is not water testing. We worked with labs early on several years ago, and they kept talking about how easy it is for PFAS in water. Well, first, I don't think it's that easy, but the sample prep is certainly pretty easy compared to paper or solid matrices. Paper and paper-coated products with residual impurities, including those that are composted or recycled, are an issue. And I know I've had folks out to my lab. I've had companies out to my lab to walk through that testing process. That is a challenge. Products can test positive for the presence of fluorine, which some analyses incorrectly identify as a definitive PFAS treatment. So there are a lot of folks out there that will tell you we can do a fluorine test, and that'll tell you definitively whether or not you have PFAS. That does not tell you definitively whether or not you have a PFAS treatment, and we have data in our lab to back that up. We've seen fluorine higher than 100 ppm that does not have a PFAS treatment, and we've seen fluorine come back at lower than 100 ppm that definitively had a PFAS treatment. So that is a concern. So and we'll get into that more in just a minute. And just to be clear, there is no strict regulation to date concerning PFAS and their precursor in packaging materials. So, we've spoken to a lot of folks, a lot of regulatory agencies about that, and this is kind of where we are as of now. So But I want to highlight again, testing for PFAS in packaging, it's not water. So when you call your labs or your private labs and have them do this, it's very challenging. So I'm just going to quickly talk about a workflow. How do we do it? So a company sends a sample to us and says, we want PFAS. We want to know what's in there. First thing we ask, are they doing targeted or untargeted? And we'll get that, or non-targeted. We'll get to that in a minute. But we start by measuring total fluorine, just to give us an idea of where we are. Are we looking at a long chain, short chain? And we'll get into that in a minute. Although total fluorine won't necessarily tell you that. It gives us an idea of, is it likely to contain a treatment? Even though it's not definitive, it does give us a marker. Then we look at what a threshold compliance is. And this varies quite a bit. There are some groups out there like BPI that do the composting work, the Biodegradable Products Institute. They determine, 100 ppm, or they've discussed the 100 ppm threshold level as being an allowable. Now I think it's 0. But yes, does it meet the compliance? Then we stop and say it's not likely to contain a treatment, or no. Then we go in to measure total organic fluorine. Then we do again a threshold compliance. And if it meets, yes, we stop. If no, we actually go into the final PFAS screening. So even before we get to that final PFAS screening, that is kind of our little roadmap. And that's one of my graduate students in the corner there. That's the extractives, and then up in the right there is the one of the non-destructive tests, and then the ion selective probe there. And we'll get into that in just a minute as well. So before I get into how we test and the testing methods that we use and some quick results, I want to just go through this slide. And I know it's busy, but I didn't know what to take out. First off, we get calls almost weekly about screening for all poly and perfluorinated compounds, or PFAS compounds. That's not practical. It does not exist. I cannot do 4,700 compounds. I couldn't do it in a week. I certainly couldn't do it in a year. So having me do that, given today's technology and methods, is not a reasonable request of a lab. Suggested non-destructive rapid methods can be used to identify surface coatings. There's some good data out there that says they can be used, but it does not. A lot of them do not screen the total packaging structure. So if you're looking at surface contact, it's an option. This is also especially problematic for multi-layer structures, and we have some data to show that as well. And my third point here goes back to what I said earlier. Total fluorine can be rapidly screened with some new technologies like the particle-induced gamma emission, combustion ion chromatography, or ion selective probe, but cannot definitively prove the presence of PFAS. So depending on what threshold level you want to use and what you want to consider as your cutoff, you're still, in some cases, going to have to go through a full PFAS screen. Here's another point that is really challenging. Sample preparation, such as grinding, milling, extractions, and handling, significantly impacts accurate PFAS measurements in packaging materials. And we have some data collected to show that. Long chain PFAS, PFOS, and PFOA results are widely variable, as high as 30% variability. And there's not a lot of standardization. So the upfront work of what is the best method to prepare a sample or do the front end work, there's really no standardization on that. So whether you're using a ball mill, a coupon, a cryo grinder, there's actually no standardization. And then we've actually worked with some NGOs and had to work with them to kind of correct some of their language and some of the environmental groups. They've been a little misleading, and I think a lot of them have cleaned up their act in the last couple of years because there's a lot of misinformation with respect to tests supposedly showing the definitive presence of PFAS testing methods and evaluation of safe limits. So they made some statements that it was tested for total fluorine, therefore it definitively contains a PFAS treatment. Again, we have data to show that's simply not necessarily true. So that can be a big concern as well. A lot of the groups we've worked with have really kind of changed that and realized that that is not a definitive test. So how do we test? What do we do? Sample comes in, we get a phone call, we're sending you some paper, we're sending you some sandwich wraps, we're sending you some trays. Great, what do you want us to do? Well, let's start with total fluorine. So I'm going to talk about testing for total fluorine. Total fluorine, if it's there, then we know that it's likely to have. It potentially has a PFAS treatment. If it's not there, it doesn't have a PFAS treatment. So if we don't find the fluorine, probably not going to have a PFAS treatment. So we look at two ways of this. We look at there's non-destructive and destructive. There's a nice technology out of Notre Dame called particle-induced gamma emission, which is an instrumental, the PIGI analysis. There's instrumental neuron activation analysis. There's X-ray or XPS. We have an XPS system. We've done some work with XPS. We do not do work with PIGI. We do that is all done at Notre Dame. And then there's some other INIAA, which we don't use as well. Then there's the destructive. We do a lot of work in destructive. That's the ion selective electrode. That's combustion ion chromatography, organic or total fluorine. And that is all of our equipment with the exception of the piece on the right that's in our lab. So we collect, we prepare, we expose, and we screen for fluorine. And fluorine gives us kind of like a waypoint on if we do or do not have a PFAS treatment. So I'm going to walk through these and quickly. So I talked about PIGI. PIGI is, we think, a very viable, it's the excitation of light nuclei resulting in nuclear excitation instead of atomic excitation. So there's some pros. It's rapid. It has a high element selectivity. It's measurement, it's minimal sample prep. You can actually see it down there in the right-hand corner. Very little interference and non-destructive. It unfortunately has some really big cons as well. It's not compound specific. It is surface limited, top few nanometers. Now, my understanding is they flip it over and do the other side, but we still think that's a surface limiting technology. It's not as sensitive as some of our gold standard LC MS or the combustion ion chromatography. It's also not really cost effective to buy one of these units. I've been told anywhere from $1.5 million to $2.5 million, and they don't have a benchtop system ready yet. But I know Dr. Peasley's group is working on that. So it's there, it's potential. We're excited about it, but it has some real drawbacks as well. In our lab, we do a lot of work with ion selective electrode. So companies send us a sample and say, boy, Keith, can you let me know, give me the heads up, give me the heads up, does this contain a PFAS treatment? A lot of times we just use ion selective electrode to tell us where our fluorine is. So we collect the sample, we cut it, we combust it, we expose it to an ion selective probe, and then we screen for total fluoride. The pros, it's rapid, it's fairly rapid. It's not as rapid as PIGI, but it's fairly rapid. It's a total fluorine measurement again. There's minimal prep, there's low cost. The cons are, again, it's not as sensitive as what we consider to be the gold standard LC-MS. It's not compound specific, it's destructive, and it's in the ppm level. So again, and it's just going to tell you if you have a fluorine, if there's fluorine present. Doesn't tell if it's a PFAS treatment, will not tell us, like all the other fluorine analysis, whether or not it's intentional or unintentional. That's another concern. And it's in the ppm level. So, you know, we've gotten down to 5 and 10 ppm with this, but that's about as good as we're going to get on a daily routine lab basis. And then we've got the LC-MS, or liquid chromatography mass spectroscopy. There's this TOPS assay, which we really like as well. It's a selective PFAS method, but it's only for PFAA precursors that can be oxidized. So 14 to 30 discrete compounds. It's not a total solution. The quadrupole time of flight mass specs combined, time of flight that result in high mass accuracy and speed and sensitivity. That works very well. And then in our lab, we are actually running an Orbitrap. So we have an ion trap mass analyzer that is both high resolution, accurate mass, and great selectivity, sensitivity, and mass accuracy. So any of these three technologies, certainly the QTOF and the Orbitrap and the LC triples work really well for us. And these are the gold standards. So this is going to actually tell you if it's a PFAS or not. And this is kind of how we do it. Target, suspect screening, non-target. Targeted, you send us a sample. Keith, I'm looking for a specific PFAS compound. You have a standard. We compare it to a standard. We inject the unknown and we compare it, and we know whether or not we have that PFAS treatment and at what level, what concentration we have it. There's also knowns and what we call unknowns. We have a library of PFAS that in some cases we can actually inject an unknown and get an idea of what we might be looking for with some help from some of our industry and customers that use us. And then there's non-targeted unknown. We have no idea. We get a lot of this where we'll get molded fiber, we'll get paper packaging, sandwich wraps, you name it. We have no idea if this contains anything at all, if it has a treatment. Again, a lot of times we'll start with total fluorine. If we hit a certain threshold level, which is usually determined by a customer, and then we'll say, well, then we need to do some PFAS screening. And if there's no idea of what it is, it gets really, really tricky. We kind of have to do a little bit of searching. So this is complex. This is complex testing. And again, this is not water. So we have to clean all of these samples up. The complexity is based on the number of compounds, precursor and fragment, and features. So retention time, mass accuracy, peak intensity, and this becomes pretty massive for computation, and I'm going to talk about that in just a minute. And I know I'm moving fast, but we've got limited time. So we have a paper in review right now that looks at the contamination sources of PFAS in food packaging. So there is little data. Actually, I don't know that I can find any data on the functional concentrations, ppb to ppm, of PFAS on paper packaging surfaces for intentional versus unintentional. What does that mean? If you send me a sample and you say this product does not contain a PFAS treatment, and I find PFAS in it, either it's a recycled pulp, it's in the paper, it's at the paper mill, and I find it, how do you know if it's intentional or unintentional? And how do we know at what concentration it actually provided a functional, it actually gave a performance feature to that paper? There's been virtually no data on that. So what we did in our work was we statistically determined the functional concentrations of some of the PFCAs, C4, C6, C8, and C10 on the surface of recycled paper packaging. Was it used as an additive or functional treatment, or was it what we call environmental carryover, whether it be from a plant, water, or a repulp paper? We did this using a contact angle measurement, so we're basically looking at the wettability of a solid material on a liquid and how well that it wets the surface. And we applied it a functional performance on different concentrations of PFAS applied to the common recycled paper substrates. So what we actually did was take strips of paper and paper that we knew what was in the paper. We treated it with stock solutions. We analyzed surface roughness using a 3D confocal laser. And then we did, and this is all equipment in my lab, then we did the analysis of the contact angle. That's our goniometer or contact angle measurement. And then we quantified it with LCMS. So again, what is the impact of this? The impact is when you look at paper packaging, what is the concentration that actually provides that functional treatment to allow that barrier? It gives it that performance that we love. So the grease doesn't come through, oil doesn't come through. That was the point of this. Or is it just carryover or environmental contamination from the recycling process or the paper pulp? So again, this is currently in review. Just quickly give you some of the highlights of our findings. As we suspected, increasing the perfluorocarbon length reduced concentration needed for functional performance. Longer chains required a lower concentration. We kind of expected that. Generally, paper packaging found shorter chain chemistries, C4 to provide functional differences at higher concentrations, 1200 ppm, compared to long chain C10 at 38 ppm. So I want you to hold those numbers kind of close to you for just a minute. What we're basically saying here is the longer chains gave us a better functionality at a lower ppm. So if you're going to screen for fluorine less than 50 ppm, you might still have some of these long chains in there that are providing some functional performance. So maybe a 30 ppm or 20 ppm is a more realistic screen. This data provides a starting point to understand and differentiate intentional versus incidental environmental contamination. And there you can see a picture of our contact angle measurement. So the perfluoral carboxylic acid concentrations associated with statistical changes in the measured contact angle performance here. Then you can see the compounds. We used avocado oil as our matrix, as our food matrix. And then you can kind of see the concentrations there and at what levels. And again, this is currently in review. But take-home message is increased or longer chains, reduced concentration needed for functional performance. And that 38 ppm was really important to us. That's telling us that we can see it as low as 38 ppm as a functional additive. And then the shorter chain chemistries needed higher concentrations. Next study that we're going to talk about. What is the effect of particle size reduction? So you send a material in and you reduce the particle size. We looked at different sulfonates, Gen X, different milling techniques, ball mill, coupon grinding, and 3 types of food contact paper packaging. So this is the techniques we used. I also want to point out that you see that chopper in the left corner? Unbeknownst to us, the blade on that actually had a Teflon treated blade. So we had to go through our whole lab and decontaminate and identify where we were getting trace amounts of some compounds, and come to find out even our chopping blade was treated. So considerations: contamination, particle size, stability, temperature, time, affinity, recovery. These are all critically important. So, and then the workflow. So again, let me just back up. We use different size reduction techniques, whether it be a ball mill or a cryo grinder, a coupon. We extract, and then we go right into our Orbi and do different types of, whether we use different types of software features to identify what we have. It's important to identify, that's actually one of my grad students in the lab there. It's important to identify 1 to 14 days of preparation. We have some techniques that we use that are 14 days, depending on the spike recovery and the aging. Water sampling requires minimal sample prep. Again, this is not water. So these are our observations. This is preliminary data, and to my knowledge, the only data we've been able to find in the world that's done this. So we actually took molded fiber, sandwich bags, microwave popcorn. We did more than this. This is the data that I had that I worked up quickly with Dr. Silva. And we looked at the differences for the analytes. Here you can see the compounds. We even included Gen X, which gave us better recovery. Ball analytical mill, blade analytical mill. We also looked at coupon. We also looked at some other grinding procedures, but these are the 2 that we pointed out. In general, the spike recovery was better in the ball analytical mill than it was in the blade analytical mill. So you can see the recovery there. But you see the highlighted areas, those are a huge concern. So the green arrows represent the higher spike recovery, comparing the 2 size reduction techniques. We used focus ultrasound. The highlighted areas are a concern. So these were areas that we found spikes, and we had what we call some residual carryover. This just shows the difficulty in doing solid paper sampling. And we have run a lot of samples. We literally run every day. And this is some of the PFAS levels we found in some of the molded fiber bowl, the brown paper, and the microwave popcorn. Again, you know, look at the differences between ball analytical mill and blade analytical mill. I didn't report our LOD here, but we're in the part per trillion. Here you can see this is we're in the ppbs, and we're moving up, and some of our data came back in the ppms. But I just want to point out that these included the Gen X, just to highlight the difficulties we have in observing paper packaging and the lab method practices that can be very different with very different results. So I'm just going to give you some of our observations. The presence of PFOS and PFOA going down in the past, 2005 to 18, but no standard methods, and this is not water sampling again. That's one of our publications in 2019 that we did on paper packaging and food and contaminants, food additives and contaminants. This issue is not going away. We have bans from 12 more states, and could be forthcoming specifically for food packaging. We're working on fiber protocols. We're working on PFAS method protocols. And generally, as I mentioned earlier, C4 to provide functional differences at higher concentrations, 1200 ppm plus, compared to long chain at lower concentrations. Increasing the perfluorocarbon length reduced the concentration needed for functional performance. I know there's some folks in the industry that already knew that, but we just kind of did that with that contact angle. Lab methods really do matter. Everything from mills to blades, this is not water. We figured out that the blades, again, just on our chopping blades, were Teflon coated. I had no idea they were Teflon coated. Our mills, we had to go back and inspect all of our mills, our cryo grinders, our ball mills. Phase separation can happen in some of the samples, another issue. Ink can yield a matrix-rich sample, so we have to deal with ink. Blade mills can generate bulky material on cellulosic samples, another issue we had. It can be challenging for sampling and mixing during extraction. It may require more solvent to cover the sample, and evaporation steps can lengthen the analysis. Again, huge issues when depending on your methods. Next steps are cleanup strategies, extraction using the accelerated solvent extraction. And really our big issue right now is developing workflows to integrate these methodologies with the analytical techniques such as LCMS. Standard methods for sample preparation. So again, if you're to call me, or like I said, we have one in review right now, and we have another publication we're working on comparing those sample prep methods. If you call me and say, Keith, what's the best sample prep method that's going to give me the best recovery and the most reliable recovery, the most repeatable recovery? That's what we're working on right now. We're using available mills, available techniques, and we're saying this is the method, this is what you can expect, and this is how you should prep your sample to get the highest recovery. And that work is, we have some of that currently in review, and we have some another manuscript in preparation. I'm going to leave you with this. I work with a lot of companies. Our research consortium is privately funded. So I work with Fortune 100s down to companies that are sub 10 million a year. Do not ignore this issue. So I gave a presentation in January pre-COVID to an industry group, and I had some folks on there saying, we're so confused. We're so, there's so much coming out. We're overloaded, and we're saying we're just going to let it go and let the regulators tell us what we need to do. You can't really do that. This is something we received, the Kroger sent out. We received it from some companies, from some brand owners and retailers. They're being very proactive, and I support Kroger in this. What are the regulations, and are you compliant today? That's really important. We're telling people to prepare for more expensive substrates, paper-based, but not if, but when, or bio-based. We're looking at bio-based, and bio-based, by the way, is not a safe harbor necessarily. We have some issues with bio-based materials as well. Some of the biopolymers and bio-based packaging, not just the paper, cellulosic paper. Work with suppliers. They're developing solutions, but they need the push to continue to do these and stay informed. And I also highly recommend you join the issues tracking group. You're here, you're with ILSI. ILSI is outstanding. Great respect for them. But AIM, Sustainable Packaging Coalition, FPI, FMI, Supermarket Sense. These folks are connected. They're working with us on methods development that we can roll out to folks to use that makes sense. Please join these issues tracking groups so that everybody stays ahead of the and being part of ILSI is so critical to that. And with that, I may have gone over a little bit, but I know I talked fast. That's me. I pointed an arrow. I don't have my video on, but that's my research team. And I just want to say Dr. Paulo Silva's in the back there, and Dr. Greg Kurtzweiler, two integral folks. Dr. Jan Shen also helped with this, and Victor and Shen. I want to say thank you so much for your time. Thank you for your efforts. And Neil, I assume you want me to jump off now, right?
Yes, thanks so much, Dr. Wurst. Appreciate the presentation. Very interesting, but we are a bit tight on time now, so we're just going to move on. I will pass presentation rights to Dr. Ginaldi. And Dr. Ginaldi, if you could unmute yourself, please. Thank you. And it is my pleasure to introduce Dr. Susan Ginaldi. Dr. Ginaldi is research chemist in the Center for Food Safety and Applied Nutrition, also known as CFSAN, at the Food and Drug Administration. Her research focuses on developing methods for the analysis of direct and indirect food additives in food and food packaging. Dr. Ginaldi received her PhD in analytical chemistry at Oregon State University and performed postdoctoral work at Environment Canada. Dr. Ginaldi will speak on method development and investigation into PFAS in the U.S. food supply. Dr. Ginaldi.
All right, thank you for that introduction. Today I'm going to talk about some of the work that the FDA has been doing on developing methods for looking at PFAS in the U.S. food supply. So just to start off with a little bit of background, there are many potential routes of exposure of PFAS to humans. In the household, we know that products containing PFAS have been used on furniture, fabrics, and carpet, and as a result have been measured in household dust. In the environment, PFAS have been shown to enter the groundwater through the use of aqueous film-forming foam, or AFFF, and also through wastewater effluent. Potential exposure through the diet is what we at the FDA are most interested in. We know that crops can uptake PFAS from contaminated groundwater, and also contaminated biosolids are also applied to fields. And we also know livestock can uptake PFAS also from contaminated water and feed. We know that since fish are a high trophic level organism, they tend to bioaccumulate PFAS through the food chain. And since PFAS tend to accumulate in protein, fish has been recognized as an important source of potential PFAS exposure. So the objectives of this research were to develop an analytical method that can be used for a wide range of food matrices. This includes dairy, meats and seafoods, fruits, vegetables, breads, grains, and then eventually processed foods. And we wanted to evaluate our newly developed analytical method using composite table-ready food samples that are collected through FDA's Total Diet Study program. So first I want to give a little background on FDA's Total Diet Study program. Currently there are 6 collection regions in the US, and twice a year each region is sampled to account for differences in seasonality. 3 cities are sampled in each region, and these cities are constantly changing. By sampling foods in different regions, we can account for differences in environmental and in agricultural practices. So 90 samples are collected twice a year in each region, which is equivalent to approximately 1,000 samples per year collected through the Total Diet Study program. So on the right side of the slide is just an example of how each composite sample is prepared. So in one region, the same food is collected from 3 different cities. For example, if we were to collect bacon, we would collect it from each city, and then it would be taken to our Kansas City lab where it is prepared as if it was ready to be consumed. So it would be cooked, and then the cooked product would be ground up and homogenized to create a composite food sample for that type. So here's a list of the current food and categories that we look at in the Total Diet Study. As you can see, there's a wide range, including baby foods, fats, oils, sweets, vegetables, and mixtures. The goal of this food list is to represent as much as possible the foods that are consumed in the average American diet. So the foods chosen for the Total Diet Study program are based on consumption data, specifically from NHANES CDC's National Health and Nutrition Examination Survey. Currently, we analyze for these analytes in the TDS program, 25 elements. We look at over 400 pesticides, 3 radionuclides, and we do look at mycotoxins in select foods. So for this current research project, we obtained 179 samples that were collected from 2 different regions of the US for our method evaluation. And this is the first time that the FDA has looked at TDS samples for PFAS compounds. So currently we analyze for 16 different PFAS compounds. We wanted to look at, the traditional short and long chain carboxylic and sulfonic acids. And, there have been previous studies showing that short chain compounds have been shown to accumulate in plants. And we do have many fruits and vegetables in our TDS samples. And we also wanted to look at some of the newer PFAS alternatives, PFAS and PFOA alternatives, Genex and Adana, which are perfluoroalkyl ether carboxylic acids used as PFOA substitutes, and the F53B PFAS alternative produced in China that contains 2 polyfluoroalkyl ether sulfonates. And some of these components, such as PFNA, PFOA, PFAS, and PFHXS, have had minimum risk levels listed in ASTDR's toxicological profiles, so we wanted to make sure that we included those analytes as well. So on the right side, I just have a sample of some of the foods that we look for. There's 91 different types, about 90 different types of samples that were collected from 2 regions. But some of them, are very, complex and different, such as, shakes, ice cream, cinnamon rolls, hot dogs. And so one of the challenges is creating a method that will be able to analyze for, such a diverse variety of samples. So listed here are 3 methods that have been previously used by the FDA for the analysis of PFAS in cranberries, milk, and fish. The most recent method that we published was a catcher's extraction analysis using a 65 ABSIX instrument, and this was looking at specifically just at cranberries. For this work, we were able to achieve MDLs from about 0.2 to 5.6 nanograms per gram. Both the milk and shellfish methods involved extraction with sodium hydroxide and methanol, followed by an Oasis wax cleanup. Both of these methods were run on an Agilent 6410 triple quad, and the MDLs range from 0.3 to about 0.8 or 1.3 nanograms per gram. So when we started to look at what method we would use for the TDS samples, we wanted to start with the method we'd used from cranberries, the catcher's extraction, and start using that for other fruits and vegetable samples. So here's just a brief workflow of what we did. So we started off with 5 grams of homogenized sample. So again, all these foods came to us table ready and cooked and washed as they typically would prior to consumption and already pre-homogenized. We then added water and extraction solvent. In this case, we used acetonitrile. We then used a catcher's extraction salt, and then the typical vortex and shaking. And then we used, for the DSPE dispersive solid phase extraction tube, we used 900 milligrams magnesium sulfate, 300 milligrams PSA, and 150 milligrams graphitized carbon black. And I do want to mention that some people have found with large amounts of PSA, when I'm saying large, I mean over 3,000 milligrams, they have shown significant loss of PFAS. But we found, and so have others who have used catchers, that when you use small amounts of PSA, it does not significantly affect the recoveries, most likely because there are other acids in the foods that are competing for these binding sites. We also used 150 milligrams graphitized carbon black, and initially, we chose this for cranberries because of the many pigments present in cranberries, and this was able to remove, pretty much all the pigments and leave a pretty clear extract. And we do analyze many fruits and vegetables that also have pigments, so we decided that we wanted to keep, this in there. We also, it's well known that graphitized carbon black is an effective sorbent for PFAS because it removes compounds with any degree of aromaticity, and that PFAS do not really interact with this sorbent. So that's kind of why we chose to keep that sorbent. We then, did the vortex centrifuging and then transferred the extract for analysis. So before we started, I wanted to see if there was some way that we could improve the method detection limits that we were kind of seeing with the cranberries, milk, and shellfish, which were, 0.2 to about 5 parts per billion. And so we decided to add a concentration step to see if that could help us, decrease our detection limit. And so we took 5 mils of filtered extract and concentrated to a 1/2 ml. And then we also tested switching from an ABSI 6500 to 6500 plus. And we actually were able to see a pretty, dramatic difference in the detection limit. So the 6500 plus is known to have an improved sensitivity in the negative mode and also improved linearity. And you can see from these graphs here that in the 6500, a 1 ppb PFAS technical standard had a signal to noise of around 16, where on the 6500 plus, we could actually go 2 orders of magnitude lower at 0.01 ppb and still have a signal to noise at 34 above 10. So we actually were able to see much lower, mostly just from switching to a 6500 plus instrument. So some of the challenges we faced with analyzing these foods was the nitrogen concentration step was effective at decreasing the MDL in most produce samples and milk, but as soon as we started to move on to other more complex samples such as meat, breads, and other dairy such as cheese, it just caused rapid column deterioration. There was just too much matrix entering the instrument. So we decided that we weren't going to do the nitrogen concentration step except for we're going to keep it for milk, since milk is a food that's highly consumed by children, and we just wanted to make sure we could see, as low as possible. But then we removed this concentration step for the other foods. We also found issues with early eluting matrix components that resulted in false positives. This was especially problematic for compounds that had one transition, such as PFBA and PFPEA. So in order to see if we could remove some of these early eluting interferences, we looked into adding a solid phase extraction step. We tried 2 different procedures. The first one was from Phenomics application note, which looked at catcher's extraction of PFAS from milk, eggs, butter, cheese, and fish. And this method used their Strata XL AW column. It conditioned with a weekly basic acetonitrile washed with water, which helps to wash out polar non-ionics and salt, and then eluted with a weekly basic acetonitrile. And one thing here that we also tried was eluting instead of with weekly basic acetonitrile, weekly basic methanol kind of as a solvent exchange, and that actually worked really well for us too. We also tried this EPA method, which looks at which is from looking at PFAS in whole fish. And they use an Oasis wax column, conditioned weekly basic methanol. And they wash with, a buffer and methanol instead of water. And I just want to point out that the buffer here was necessary because these samples were alkaline extracted. So you have to use a buffer so that the ligand doesn't get neutralized prematurely. But I wouldn't have that issue with our samples because we are not using an alkaline extraction. So here's the result of some of the before and after the wax cleanup. So in the top left, you can see the catcher's extract. And you can still see in the very beginning of the chromatogram, those are all early eluting interferences, matrix interferences. When we looked at in the top right, the EPA method SPE, we still saw a lot of those early eluting interferences. But when we used the protocol in the Phenomics app note, we actually saw most of them were completely gone. So that method, SPE method, was really effective at removing, whatever these matrix components were. And I just wanted to note that we did test the Oasis Wax SPE column with, the sample wash and elution steps listed in the Phenomics app note, and we found that the brand of SPE sorbent didn't necessarily make a difference, but the difference was due to the choice of wash and elution solvents that were used. So here's an example of a bread sample that shows a false positive detection of PFPA in the catcher's extract. So since PFPA only has one transition, it's difficult to confirm it's present when you're using triple quadrupole. Other people have used, an exact mass or Q-exactive instrument to confirm the presence of this compound in samples when they have found it. And so we wanted to see if this SPE step, would help remove this false positive, and it did. And so we were able to confirm that PFPA was not present in the sample. So we then performed a single lab validation on 4 different representative matrices. So for dairy foods, we chose milk as our matrix. Produce, we looked at lettuce, and then meats and seafood, salmon, and then for grains and baked goods, we looked at wheat bread. So we used 2 different brands of each matrix from a local grocery store, and we spiked them at 6 different concentrations, ranging from 0.25 parts per billion to 25 parts per billion. And for all of these food samples, the coverage fell within the required ranges. And I did want to mention that, all samples are quantified using isotope dilution mass spectrometry, and we do add H surrogates to the samples prior to extraction. So all of these results are recovery corrected. So we also looked at bread before and after the wax cleanup just to make sure that this didn't have an effect, on our recoveries. And we found all the recoveries were in range except for one of the components of F53B. We found it had a slightly lower recovery, about 33%, and for the concentrations, we were looking at needed to be above 40. So we determined that this method, was not suitable for that compound, particularly in just the bread matrix. So here is a summary of how we adjusted the method in this top table based on the matrix. So I mentioned we had added water to the catcher's food, and for bread we ended up having to add 15 mils of water, and this is just to swell the matrix, since these food samples, typically are much drier than produce, dairy, and meat samples. For milk, we performed a nitrogen blowdown, so we took 5 mils of extract and blew it down to half a mil. And then for cheese, we had to reduce the sample size down to 1 gram because we found that cheese had, large amounts of matrix that would also deteriorate the column rapidly. So we calculated these method detection limits using the EPA method that's cited in the CFR, the Code of Federal Regulations. And so in the second table here, you can see for the different matrices and the different analytes, what we calculated these method detection limits to be. And they're pretty consistent for bread, lettuce, and salmon. They all range between about 20 and 100 parts per trillion. For milk, we were able to see lower because we are, doing that extra concentration step. And then for cheese, the method detection limits are higher because we are only using 1 gram of sample as compared to 5. But compared to, our cranberry method, which had method detection limits of 200 to 5,600 parts per trillion, the TDS MDLs were much lower. And again, this was mostly just switching to the 6,500 plus versus the 6,500. So the MDLs here are all well below concentrations that we would expect to be of concern in food. So here's a summary of the results of the samples. So we looked at 179 different food samples from 5 different categories. And out of all of these samples, we only had 3 positive detects. We had tilapia samples from each of the 2 collections that had positives, around 83 and 87 parts per trillion. And then ground turkey around 86 parts per trillion. So the presence of fish or PFAS in fish, which is a high protein, high trophic level organism, is not unexpected. Others have found, previous studies have found PFAS and even in tilapia at, around 200 parts per trillion. And other studies that have looked at total diet study samples, such as in Canada, have estimated that meats contributed to 90% of the dietary intake of PFAS. So the findings of the PFAS in tilapia and ground meat, were not surprising, and they are quite low, still under 100 parts per trillion. So in summary, we single lab validated a method for the extraction of PFAS in produce, dairy, meat, and bread samples. We then analyzed around 180 TDS samples to evaluate the method. We are going to continue to analyze TDS samples. We also have around 200 processed food samples that are also collected once a year as part of our TDS food program, and these samples are different from the regional food samples. And we are also might have to make, method adaptations if needed with future matrices. As we saw with our method, we did have to make adjustments as we moved into, more complex food samples, and processed foods will probably be, even more difficult. We're also looking into potentially adding some other analytes, such as fluoropolymer sulfonates. And, as we move into the processed foods, there are some, we will start looking at popcorn, from popcorn bags. And so we might be interested in looking at some of the PAPs and DIPAPs, the polyfluoroalkyl phosphate esters. So thank you for your attention, and I'll be happy to take any questions.
Thank you so much, Dr. Ganaldi, for this interesting presentation. Dr. Ganaldi, I do have a question that came up. What is next for the FDA in this space, and what is your plan to extend the testing to other food samples?
Yeah, so we're currently working with one of our ORA labs, which is our field laboratory, and looking to have them start running our method and having PFAS kind of added to our total diet study list of analytes, so that we will start monitoring them on a regular basis in all total diet study food samples. And then, like I mentioned, we will be looking at the processed food samples as well.
Thank you. Another question, is the FDA studying the leaching of PFAS compounds from food packaging into food?
So we have done some work previously on that in the past, and we are actually, we have a postdoc starting in about a month that's going to start looking at PFAS and packaging in a little bit more detail and, in migration studies and that kind of thing. So we're not doing it currently, but we are looking to start it in the near future.
Here's another question. Have you given any consideration to farmed fish versus wild-caught fish in your analysis?
Yeah, so the fish that are included in the total diet study program are fish that are most the highest consumed. So based on NHANES data, so the the tilapia, most likely was farmed. So that would depend on kind of what the most highly consumed seafood species are, but whether they were farmed or wild caught. So that's kind of, but we haven't looked, specifically into differences in farmed or wild, just kind of focused on, what fish are currently included in the total diet study samples.
Let me introduce you first. So Charles Nestland is a scientific officer for Eurofin's Lancaster Laboratories Environmental and the PFAS practice leader for Eurofin's Environment Testing United States. Charles has worked in environmental analytical chemistry for over 36 years. He is a subject matter expert in high-resolution mass spectrometry and PFAS analysis. Charles initiates new methodology and directs research and development at Eurofins. He is also responsible for identifying trends in analytical testing and equipment at Eurofins. Charles will speak on challenges associated with analysis of PFAS in food and food contact materials. Take it away, Charles.
Thank you, Neil, and thank you and ILSI very much for inviting me to present here today. And also I wanted to thank Keith and Susie. I think their presentations were terrific. So thank you very much. And I think folks will see that as I go through, there are elements of what I'm talking about that tie into both Keith and Susie's talks, what to me is always the fascinating thing for all the years that I've worked in environmental and analytical chemistry is how different folks from different walks of life and different disciplines come across and to the same end objective as one another. So anyway, with that, a little bit of intro or to give some perspective on PFAS. I know both Susie and Keith did at the beginning of their talks, their discussion, but to point out, we talk about PFAS, but PFAS really formally is a very large group of materials, and Keith mentioned 47, greater than 4,700. Well, those are actually, the greater than 4,700 are actually the non-polymeric forms that we know are potentially out in the environment and potentially in contact with food, water, and other things that we consume. Polymeric forms are also formally PFAS, although the polymeric forms, the ones that we're familiar with regard to Teflon, FTFE, PTFE, other fluoropolymers like that, which are so essential to many aspects of our life, are also PFAS, but not what we're currently concerned about in our food products, in the environment, in our drinking water and like. And even within the non-polymeric forms, there are multiple classes of compounds to be concerned with. In that total list of 4,700 compounds, under that, we actually have several broad chemistries like anions, cations, zwitterions. There are also neutral compounds like fluorotelmer alcohols that are acrylates that are potentially of concern. But most of what we're talking about here today and the analytical methodology that we're talking about is addressing the anions and those things that were used in AFFF, other surfactant processes used in the manufacture of polymers. So despite the concern for PFAS in drinking water, And as you know, Keith pointed out, drinking water is a lot different, a lot easier than the packaging material. I think there's some of us that might disagree with a little bit. I think there are elements there where it's different. It's a different game. In drinking water, we're looking at extremely low levels, and in fact, when we're talking MDLs, there we're at sub PPT concentrations for many of those if we get down to an MDL level. But they bioaccumulate. They can be found in the food chain. Typically see them partitioning the protein, and not like other persistent organic pollutants that we've had to be concerned about in our food chain, like dioxins, PCBs. Those are all lipid soluble and lipid seeking, whereas PFAS are not necessarily so. And the big concern is that they're not metabolized, or if they are a form like a polyfluorinated form and they do metabolize, they typically go to a more terminal form of PFAS, like the perfluorocarboxylic acids. So from a bioaccumulation standpoint, and this was an environmental paper. I know we're talking food here, but in an environmental paper, because I think this applies, if you look at this longer PFAS or longer chain, which was mentioned in earlier talks, are more bioaccumulative in animals. And you see the chart over there on the right where the shorter chain, like the butanoic acid, the pentanoic acid, are less bioaccumulative in animals, whereas the longer chain, say an octanoic acid, an octane sulfonic acid, the nonanoic acid, so a C9, those are more bioaccumulative in animals. But in plants, it seems to be the opposite situation, where you tend to see if there's some bioaccumulation. And from an absolute amount of bioaccumulation, I think we're looking at an order of magnitude or so different. But you typically see the shorter chain, the C4, the C5, that tend to be bioaccumulate in plant material more so than they do in animals. So much of what I'm going to talk about here next is really talking about this from the point of a contract laboratory. So in our case, you know, we go to contract laboratory, so it's a commercial need, a commercial endeavor, and also we're, for the most part, where there are published multi-lab validated methods, that's what you're expected to use. That's what you're expected to be certified, and what your quality systems are built around is those multi-lab validated methods. Well, when we first started doing PFAS, and actually for the drinking water method back in 2008, 2009. And then as PFAS became environmentally much more of a concern at certain sites in the 2015, 2016 kind of time frame, I mean, what reference point do we have? Our reference point is an EPA method for drinking water. So that's what we know. That's what we are familiar with. That uses a solid phase extraction, which was some of what was talked about earlier in Susie's discussion when she talked about those wax cartridges. But in this case, they used a different chemistry. EPA used a different kind of chemistry, something called a styrene divinyl benzene. And there it actually functions based on hydrophobic interactions. So if it's a hydrophobic interaction, that long tail of a PFAS compound, whether it's a C8 or a C9 or a C10, those compounds are adhered to really well. They extract really well. But when you get down to shorter chain compounds like the C4 and the C5, that kind of chemistry just doesn't work as well for extracting them out of water. But the main intention of the current EPA method 537.1 was originally to address PFOA and PFOS, for which there were some health advisories set in drinking water, and then more recently to add in these replacement compounds, Gen X, or you'll see the acronym HFPODA, ADANA, the F53B major and minor, that were replacements for PFOA, PFOS, to a certain extent PFHXS, in some of their common industrial applications. So for the most part, that's where, if we're going to have to do matrices outside of drinking water, where's a contract laboratory going to go? They're going to base it on what they know, what they're certified for, what's multi-lab validated, and then modify to be able to address the other matrices. Just recently, the end of last year, EPA put out a new drinking water method, but still drinking water, and that was 533. Uses SPE also, but has gone to this wax or weak anion exchange chemistry for the extraction. And here the advantage in that, and you'll see in the other applications, in the application we set up within our laboratory, we use that weak anion exchange chemistry for the extraction, because it takes advantage of I'll call it the head of the molecule, that carboxylate anion, the sulfonate anion, excuse me. And so we get better selectivity on that extraction, and also think that we can extract a wider range of PFAS compounds. So then there's the EPA 533 method out there. I know this slide's a little bit small, so bear with me, but I was trying to show you. So if we look across a list of compounds, here are the kinds of compounds we've got that are covered by the drinking water methods: carboxylic acids, sulfonic acids. There are a couple of sulfonamidoacetic acids. The newest method has some of the fluorotelmer sulfonates, and then also some of these perfluoroether carboxylic acids that are some of the replacement compounds. So the commercial laboratory like ourselves, what would we do when we're asked to do food, asked to do vegetables, fish, some of the various kinds of products that Susie mentioned? And for us, it wasn't that we were going out and doing a market basket study or a survey. We have clients that have a concern. They learned about their dairy cows drinking water that they learned now was contaminated with PFAS, or eating from fields in which they had applied biosolids, or vegetables that were grown in fields where biosolids had been applied, and or irrigated with PFAS contaminated water. So that concern is, we need you to look for these compounds. Do you have a method? Well, again, 2015, 2016, there aren't published established methods. And what Susie showed that FDA has done more recently is terrific. And what we're looking for then is multi-lab validation, and what Palmer's going to be talking about here in a few moments. But anyway, so we would set up a method using what we know. It's LCMS-MS. It's a targeted compound analysis. We're going to use isotope dilution, and that was mentioned previously, and I just want to talk a little bit about that, because I think the isotope dilution is what is really strong for getting us through these various matrices. So isotope dilution, very simply, is where we've got a compound that is essentially exactly the same as the target compound that we're analyzing for. So in this case, I'm showing a C13 PFOA, and you see I have a couple of the carbons there that are C13. Most carbons are C12. 98.9% of all carbon is C12. Well, if we've got these isotopically labeled compounds, this C13 PFOA, and in this case there's 4 C13s, or there could be 2 C13s, or 3 in that structure, depending on how it was synthesized. It extracts out of a matrix like my native PFOA. It's going to chromatograph like my native PFOA. It gives me a retention time marker for my native PFOA within the sample matrix that I'm analyzing. So it is as if I spiked the sample with PFOA, but because it's the C13, its molecular weight is just a little bit more than PFOA. So with our mass spec, we can discern the difference between those. So then doing that, and here's another small So if I get yelled at for anything today, it would be that I've got these slides with a lot of small writing on it. But wanted to show you, so this expansive list that we're able to do, and if you look down the column with the check marks with most of the X marks in it, is what our routine list of 40 compounds is. Now these are targeted compounds. This isn't getting into some of the non-targeted work that Keith was talking about, but targeted compound lists that we're able to do and use an isotope for most all of those, not all, but most all of those, able to use an isotope dilution application. So not, like I said, not a lot of validated methods. So the approach that we would decide to do, or that we're asking, what would we use for vegetables, fruits and vegetation, dairy, meats, all those kinds of matrices? We're going to want to use something that, number one, is isotope dilution, because it will show us the actual recovery of the target compound that we're interested in that specific matrix. So in the absence of a multi-lab validated method, or a method that has been built and developed specifically for cheese, or specifically for fish, or specifically for carrots, we've got a way to get a great handle on the performance and extraction performance of these compounds within each one of these matrices. So we also then take advantage of the weak anion exchange chemistry. So much of what you heard Susie talking about, which is we extract it, we blend it with some organic solvents, and then remove that from some of the residuals. What we also did was we used a sorbent and a binding agent. So we would blend it with a binding agent, which a lot of the pigment, a lot of proteins, a lot of other high molecular weight materials that were potentially going to give us problems would bind to this binding material. Then we used organic solvents to pull the PFAS off of that blended mixture, and then took that solvent mix, concentrated it down, and then we would put it through a weak anion exchange cartridge for an additional extraction, isolation of the PFAS, and in some cases, depending on the material, include PSA and or a carbon-based cleanup. So you see the commonality with what Susie had set up, and this is something that we had set up and worked on several years ago to be able to offer to clients and customers. But look at the commonality between, and honestly, before this interaction, Susie and I didn't know each other, but yet we've come to, I think, relatively similar or common places in this method. So in trying to move along here, here's another lot of a busy slide, but it's a 2-page raw data piece just to show you where we've got this list of these isotopically labeled compounds, the extraction standard peak table that I have over there, and their recoveries in this particular matrix, and then your targeted compounds analysis, for which all of those results, you see some low-level detections in there, but nothing that quantified above what the MDL was. The other thing to point out is that is a concern here. The targeted analysis with LC-MS is a terrific analytical technique, but as we've gained experience with these, or we've learned some things like, for example, this was from the analysis of eggs. So with eggs, we were seeing this peak, and you see on the, and this shows as PFOS, but in the middle plot there, that transition from 499, mass 499 to 80, you see a peak, it's not shaded in, and it's shifted over to the right. Well, looking at this, and you think, oh, well, maybe that was just a little matrix that shifted that peak over a little bit. Well, actually, this is a chromatogram of a bile acid, taurodeoxycholic acid, which in things like eggs can become a problem and produce a false positive if you're not aware of the possibility for that potential false positive. I mentioned fluorotelomere alcohols, so I mean but again, to point to the fact that PFAS, not all PFAS are anions, not all PFAS can be done by LC-MS, not all PFAS can necessarily be done by the exact same, even if it's an exact mass, the exact mass analysis, because sometimes these cleanups that we talked about before they perform essentially a discrimination on your sample based on whether they're anions, cations, neutrals, what have you. So you have to be cautious about what kind of extraction and processing you're doing of your sample prior to that analysis. And then these things have already been brought up, but again, as a commercial laboratory, these are things that we have or have worked on putting in place for our environmental clients, but they found great use for clients that have food products that need to do the analysis. And the total oxidizable precursor, just very quickly, is really where it says it allows us to use our targeted compound analysis, but it says there are potentially compounds present in your sample matrix that can be forcibly oxidized to the perfluorocarboxylic acids. So I can analyze for the perfluorocarboxylic acids really well. Some of these other compounds I might not know or be able to see, but under laboratory conditions, I can sort of force the oxidation of them to these perfluorocarboxylic acids, which then gives me an indication that there are other PFAS present that I may not be able to specifically target or see, but would have some sense of being able to detect their presence. And then the total organic fluorine combustion ion chromatography, which Keith mentioned, which can be applied to water, solids, soils. So I'm not going to spend a lot of time there. And then, of course, the non-targeted analysis, which is a new area for us. We in fact are using a QTOF, not an Orbitrap, but a quadrupole time of flight mass spec that can give us exact mass and can do all of the kinds of things that were talked about before. Basically finding knowns and what we're calling known unknowns, those that might be found in our limited libraries. We've got libraries of hundreds of compounds, fluorochemical compounds, not the tens of thousands like we have in other GC mass spec libraries, but something that could help us to do an initial sweep, and then of course isolating it to unknowns. And with that, I think I ran a little bit over, so I do apologize, but I want to thank everyone for their attention, and thank you for the opportunity.
Thank you so much. Interesting presentation, Charles. We will now keep going in the interest of time, and we are hoping to have time for a joint Q&A at the end. So I will now make our last speaker, Dr. Orlandi, presenter. And while we're getting set up, I am looking at all the questions that are coming in, and I have them in front of me, and I've prioritized them. There's a lot of them, a lot of good ones. I apologize in advance. We won't be able to get to all of them, but we will try to answer the ones that I think are of broad interest to the audience. And if we don't get to your questions, you can reach out to me later, and we'll make sure to forward them to the speakers and get your questions answered to you at some point. So it is my pleasure to introduce Dr. Palmer Orlandi. Dr. Orlandi is a Deputy Executive Director and Chief Science Officer at AOAC International, and he is also responsible for overseeing the AOAC Research Institute, standards development activities, and the proficiency testing program. Dr. Orlandi also handles business development responsibilities, including developing strategic partnerships with the goal of advancing voluntary consensus standards and strengthening international relations. Dr. Orlandi has extensive background in government relations, food science, food safety, regulatory affairs, and public health in the federal government. Prior to joining AOAC International, Dr. Orlandi served more than 22 years at the United States Food and Drug Administration, most recently as Chief Science Officer and Research Director in the Office of Food and Veterinary Medicine. Dr. Orlandi will speak on developing international consensus performance standards and official methods for analysis for PFAS, benefits and challenges. Dr. Orlandi.
Thank you very much, Neil. Before I begin, I want to express my my gratitude and thanks to Neil and Wendelin and all the ANSI North America staff for allowing me to participate. I don't think it will be any benefit to repeat the excellent information that we heard in our first 3 talks from Keith, Susan, and Charles on the PFAS landscape. We've already covered things such as the extensive amount of registered substances, the fact that they are forever chemicals and persistent in the environment, that they're bioaccumulative, their chemical properties, and the broad industrial and food applications. Just to reiterate, however, the flow from the sources of contamination through how they actually get into our food and potentially cause public health problems. And this ranges from the ocean being the largest reservoir for these contaminants relating in seafood contamination, their absorption into soil, the effects landfills have on the groundwater, and then eventually through both our seafood, fin fish and shellfish, our agricultural fresh produce commodities, and then through contact surfaces. Like I said, we've already heard the origins of it, identifying the knowledge gaps for the prevalence and exposure data, and identifying the current analytical testing gaps. What I'd like to do in closing this session really is to provide some insights in how to address those analytical testing gaps. There are many. Again, they were more than adequately highlighted by Keith, Susan, and Charles. And then to also talk about the significance of consensus standards. Where do the consensus standards and methods development and the global integration of these products fit in addressing not only just general analytical needs, but specifically where PFAS is concerned? So let's talk about some of the analytical challenges, particularly in the food industry and for regulators and analysts alike. It always comes down to what is the method of choice? What's the breadth of applicability? Is it a multi-analyte capability? What are the matrices that need to be addressed? Not all matrices are alike. That was particularly highlighted by Keith when he constantly reminded us that foods are not water, and there is a complexity and a heterogeneity in such matrices that need to be considered when we talk about the performance and the choices of analytical methods. What is the availability of comprehensive validation data? Another thing that was hammered home, particularly when we move from methods that are used in a research application to methods that are used to support surveillance, compliance, regulation, and broad acceptance. This also involves the technologies that are used, the technologies that may be available to certain regions of the globe versus the applicability of technology that is much broader based. And then we can get down into the nuts and bolts of the methods, such as the disparity in performance requirements that may need to be addressed based on where your products may be produced, exported, or imported, the disparity in regulatory requirements, and the changing and rapidly evolving scope of the need. These are some of the general considerations that whether you're a contract lab, whether you're a regulatory lab, or whether you're a method developer or in the technology sector, these are the general things that need to be considered. So what did we hear today? Well, we certainly heard of the extensive work that the FDA has done in developing a single lab validated method for foods, something that is severely lacking. In fact, it is the FDA method that is the only validated method around there. Hence their drive to incorporate greater matrices into the validated schemes, and also to incorporate that into their dietary surveillance programs to look at the scope of contamination or the presence of PFAS in a variety of processed and unprocessed food products. To reiterate, they have now validated in their method 16 compounds with 4 or more commodities that started with bread, milk, salmon, and lettuce to encompass grains, dairy, seafood, and fresh produce. However, as we've heard, there are considerable gaps in food and food packaging based on the complexities that each of these types of commodities or new commodities will present in getting a very good evaluation of the levels of PFAS presence in these commodities. Added to that, there is limited international consensus on performance standards and validated methods for analysis for majors beyond those that are already accepted for water and soil testing. Again, something that we heard repeatedly in our first 3 talks. So I've used the word consensus many times already, and you're going to hear it again as we get through this. Well, what really do we mean by consensus? And really, the basis for consensus is it's a general agreement. It's a judgment that's arrived by most of those individuals or groups that are involved. It's a way of creating solidarity in sentiment and belief. Now let's move that definition onto the analytical sector. What are analytical standards and what are the benefits in achieving consensus? Well, the consensus for analytical standards really, they begin by documenting the need for an analytical method or performance requirements for that method. And it provides a detailed description of how that method must perform. Again, through consensus. It includes method acceptance. It also includes a variety of different criteria that go along with it, not only to describe how a method must perform, but consensus in analytical standards, consensus in method development, and anything that follows from that really requires a set of achievable and consensus criteria that everyone can use as a roadmap to move forward. And lastly, encompassing all of those, it's an agreement among stakeholders and subject matter experts to achieve what was documented as the original need. Standards development are really guided by 3 general principles. And then sub-principles that define the entire process. We talked about consensus and really what defines consensus, but it also incorporates 2 other concepts, defensibility and acceptability. Defensibility is that there is enough information there and agreement in consensus that the results can be defended. It's also based quite closely to consensus with acceptability, where those involved in developing those standards agree that the data achieved from those methods are acceptable for use over a very broad range of stakeholders. Buried within the standards development principles, there are 7 other categories that I just like to just identify for you. Because they are the hallmarks of what consensus in standards really are. And they involve transparency, openness, balance of interest, lack of dominance, due process, again, the word consensus, and an appeals process for those within the stakeholder communities that may take issue with the final outcomes and give them due recourse for reconsideration. Don't have to really go into what these mean because they're really self-explanatory. But what I do want to highlight is one in particular, and that's the balance of interest. And that really is the foundation for driving consensus. The balance of perspectives, at least from AOAC's point of view, is it provides a map of the stakeholders who are buying in and contributing to the process. And this breadth of stakeholders and balance of perspectives may vary. And this is just one example that I've included in this table, where we have broad perspectives, specific perspectives, and regional perspectives based on what that subject may be. And such stakeholders, all of which here are active members of the stakeholder communities within AOAC, include global, they include discipline specific, they include government, industry, and academia, industry specific, such as food and beverage, reference material providers, regulators, researchers, and the like. It is these types of perspectives that come together to give a very well-rounded product through the process. Now, standard development organizations as a whole, as Wendelin pointed out for ILSI North America, are largely fall within these 5 characteristics. They are usually independent third-party organizations, they're nonprofit, they develop criteria for conformity assessment in one form or another. They are largely described as conveners of subject matter experts who are tasked to develop solutions. They don't develop the methods, they don't develop the standards. They identify through their stakeholder engagement that there is a need. In the case of ILSI and AOAC alike, they define in the food safety area where we're concerned that there is a problem and there is an issue. And then they convene the subject matter experts and drive the process forward. They have no vested interest in the outcome. They are agnostic to it. But it is the subject matter experts along that broad perspective of stakeholder communities that bring the solutions to the table. So AOAC, in this particular instance where we're talking about food safety and PFAS contamination in food and food packaging, we offer a science-based organization to develop analytical solutions, develop standards for microbial and chemical methods. We deal in the food safety and food defense space. We have broad stakeholder involvement that includes a wide breadth of stakeholder communities, that balance of perspectives from industry, laboratory, government and regulators, academia, technology centers, and as equally important as in any of those other sectors, our peer standard development organizations, such as ILSI North America. As a whole, the products that we put together in collaboration with our stakeholders is to promote that global and regional trade and to facilitate public health and safety. That's the ultimate goal. These are issues that transcend specific particular needs, but are so broad that they affect a variety of different global and international processes. And so what I'd like to do in the remaining time is to use this foundation, what I have described about consensus, SDOs, and AOAC's insertion into the food and food safety space to talk to you and outline the processes of standards development and methods development and the value that such a process, particularly in light of what we've heard in our first 3 talks, about the value of this process moving forward, actually the need for this process. And then also, and hopefully to present to you the larger benefit that standard development with stakeholder involvement can help address the global concerns for PFAS contamination, particularly when we're talking about its presence in food and food packaging. So AOAC International, and again, I'm going to use standards development from our perspective since this is essentially our bread and butter. Our standards, also known as standard method performance requirements, form the basis for the adoption of official methods. Such standards are used to evaluate and confer official method status not by AOAC, but by expert review panels that serve to support AOAC in this spot. And you could insert any other standard development organization in any other area of expertise. These are driven, again, as I said, by experts. And then these standards and the official methods are published and available for use and incorporation by stakeholders, not only those that are or were involved in creating those standards, but those who can use those as a consensus model for carrying out analysis, either by regulators, contract laboratories, or other bodies. So what does a standard look like? This is, again, a typical SMPR from AOAC. And I know you can't read this, but I'm going to highlight the regions, the breadth that covers how a method that is developed based on their standards, what that method must abide by or should incorporate to be considered an official method of analysis. These include the specified intended method use, how that method is to be applied, what areas is it applicable to, what are the definitions to make this understandable, and how does it relate to the method. Most importantly, the performance parameters and the targets that the method must meet. This includes recovery, the analytical range, the limits of detection, the limits of quantitation, and so forth. And then, equally importantly, it is defining the commodities for which any method that is developed based on these standards must specifically address. So to use the example that Susan provided, if there were an SMPR for PFAS in foods, of which there is not, only within the regulatory realm for FDA. These are commodities that would include dairy, produce, seafood, grains, but not just the categories, but the specific commodities, as it is well recognized that many methods may not apply to all foods within a particular category. What about the concept of this standards development put into practice? Following the guidelines established for standard setting organizations and the practice of engaging our stakeholders and identifying the need, it all begins with an advisory panel of stakeholders that have a vested interest in overcoming an analytical challenge. It is then the part of the standard development organization, such as AOAC, to then bring in subject matter experts who are method developers, who have a knowledge of the chemistry involved or the microbiology involved, the pathogenicity, the genetics, so forth, to begin working to draft how methods to detect that particular analyte need to work. This is done through a series of meetings, and I should say, whether it's not intuitive or not, these are all volunteers. Our subject matter experts have day jobs. They work in laboratories. They work in academia. They are captains of industry. They know the fields, but they are working as a whole to develop solutions to a common question. That the work is then presented for public comment. Think of what is usually put out by the federal government in the Federal Register. We operate very much in the same space. where the products, the standards are drafted, and then they're provided to public comment beyond the stakeholders who drafted the standards. And then we work to develop community consensus on a much larger scale. And it's at that time, once consensus is achieved, ensuring that there is broad stakeholder involvement in achieving that consensus, that standard is then deemed final and published. This is normally, for AOAC in particular, a 6 to 9 month time frame for the generation of one SMPR. That's not to say that multiple working groups in different areas of within a specific point of contention can't be worked simultaneously, but each SMPR usually takes between 6 to 9 months at the outside to go from presenting the work, assembling the work group, and reaching and publishing consensus. As you may be aware, this is really just the beginning. Putting into practice the whole process does not begin and end with the development of a standard. That's only the beginning, and there is a need now to field methods that address the performance standards that have been agreed upon to accomplish their mission. And that's a call for methods, and then an assembly of an expert review panel to evaluate those methods which have been submitted in addressing the standards. And once again, those methods need to be evaluated by a panel of subject matter experts, resulting in first action, which is essentially the first step in final approval of the method. And in this process, we ask our method developers to demonstrate reproducibility. That's the first step to achieving overall adaptation and adoption of this particular method. Final action requires multi-lab validation, a collaborative study beyond the single laboratory. I mentioned validation now as the key in moving forward in methods that have been adopted based on standards. A method, it all starts with what validation actually means. It is this key to adopting and agreeing on the integration of a method and consensus to make it an official method of analysis. And it's based on the performance of that method, including, in particular, its precision and its consistent capability across multiple laboratories, using a defined consensus on validation criteria. This can be done both at the single lab validation step, as is required for our first action of an approved method, or the reproducibility in a final action, which characterizes the method performance across multiple method users. Now, I realize that there are many who understand validation and the criteria upon which validation exercises are based. These are the same types of criteria that were used to validate the FDA's method. The same holds true in standard development organizations such as AOAC, where it is important that not only we achieve consensus when we talk about standards and consensus on method performance, but it also includes a consensus on what it means for a particular validation study. And lastly, going from the consensus of your stakeholder communities to the global community. It's this consideration for the international harmonization and consensus. And again, highlighting those goals based on how AOAC operates in this space. I mentioned AOAC's work with other peer standard developing organizations, the principal of which is ISO. And we engage with ISO in a number of agreements where we act as an accredited technical advisory group within the US for food products. There's also the official liaising within ISO technical committees and subcommittees, and the door swings both ways. We have active participation of ISO within our working groups. It also expands to other types of organizations, and highlighting the collaborations with the International Dairy Federation, again through AOAC and ISO. There is a distinct link between ISO, IDF, and AOAC as we work to provide methods and jointly submit them to Codex. And Codex, as many of you may be aware, looks at the incorporation and the identification of methods for Type 2 designation, dispute resolution status. And it is important to understand that as you go from consensus standards to method development through collaboratively validated methods to adoption into a global body such as Codex, it creates that framework and that foundation by which all agreeable will use and accept the data by using those methods. At the same time, it is not just methods, but again, it's talking about criteria for evaluating, and it's whether it's evaluating the method or evaluating the processes within a laboratory, all encompassing to create a very harmonized quality system for laboratories and for a variety of other stakeholders that are dependent on the analytical results that come from the methods developed. And so in closing, I want to just use one quick little visual here. I talked about the benefits and challenges, and not necessarily from PFAS, but how it may relate to the challenges presented by PFAS. You've heard in the first three talks a myriad of challenges. We have capabilities that already exist to begin analyzing with great competence PFAS contamination in foods, food products, and packaging, to assist in surveillance, to assist in risk assessments. We are starting to make our way. The benefits, however, the larger benefits, really come from overcoming all of those challenges. And what I'd like to at least reiterate one more time is to overcome these challenges as a complete stakeholder community, stakeholders that we have identified multiple times over the last 2 hours. You have to reach consensus to overcome those challenges. Those will be the benefits that you will realize. And so with that, I'd like to thank everybody involved, particularly again, ILSI North America, Neil and Wendelin, and thank you very much for your attention.
Thank you so much, Dr. Orlandi. Interesting presentation. We have a few minutes for questions, and I've also asked our organizers if we can go a little bit over time if there's a need. I have received a lot of questions, and I have been working to combine them by themes. And if I don't get to your question, I apologize, but we wanted to sort of focus on the question of broad appeal. So with that, I'm going to ask a question that was directed at Dr. Vorst. Going back to the measurements of PFAS, what are the actual concentrations that actually migrate from the coated paper into the food? And along those lines, what conditions can affect those migrating concentrations? For example, if you go back to the example of the French fries in the paper, will the temperature that the fries sit in the paper would affect how much migrates or other conditions? What can you comment?
Okay, can you hear me again? I
Yes.
think I'm on mute. So we typically, when we look at migration, we typically look at what we consider to be condition of use. And we do a lot of testing on whether it be a French fry, a popcorn bag, on the actual condition of use based in the CFR protocol, usually the 21 CFR. And the chapter 1760 is one we just did yesterday, as a matter of fact, for extractables. And that will impact, so lots of things impact migration, the coating, the depth of penetration, the how it's applied, the manner in which the condition of use is it a microwave product? Is it a heated product? Is it a dual ovenable? Is it a, and contact time. So the food side, the FDA is they're the experts on that. On the packaging side, and I think they've done a lot of work on that as well. But I don't know that there's a lot of data. As a matter of fact, I know that we're actually working on this right now because there isn't a lot of data on just how long and at what coating level could you expect to see a migration. That's actually that's a next step for us. To look at potential exposure. I want to make it clear I'm not a toxicologist, but we can certainly identify how much would come out or be available for consumer exposure depending on the condition of use and the type of material and the amount of the application, the concentration of the application. I think it's also, one thing I didn't talk about is some of these chemistries are processing aids and part of the polymer matrix. So that's also, again, condition of use is critical.
Thank you. Another question pertains to plastic. Do you measure PFAS in plastic, and in particular plastic used in packaging? And also along those lines, extending this to paper, how much do you measure, do you expect to measure in recycled plastic or recycled paper?
That is an excellent question. Yes, we have found these chemistries in plastic. And I think it's important to say we do a lot of work on PCR, post-consumer recycled plastics. That's one of the some of the survey work we're doing right now. But we work with a lot of companies that say, well, I can move out of paper into plastic and I can avoid the PFAS problem. That's not necessarily true. We have found it in plastic. We've also found it in as some of the residual in plastics, whether it be a paper coated or a treatment to the an adhesive treatment. But yes, we have found it in plastic, and plastic is not necessarily a safe harbor. Also, it's important to note that plastic is currently is one of the targets right now. So we're working through paper, but plastic is also being evaluated as well. And I don't have, we've done the work. I don't have the data in front of me, and I would be at a loss to throw out some numbers. But I do know that we have looked at recycled plastic, and we have found it there.
Thank you. Question for Susie. Have you or are you planning to analyze microwave popcorn?
Yeah, so in the set of around 200 food samples, that is the processed food that we're going to start working on next. One of the highly consumed foods is microwave popcorn. So yes, it will be included in our future analytes. Okay. Food matrix.
Thank you. Question for Dr. Orlandi. Is there currently an AOAC working group for PFAS in food?
No, there is not. It's certainly an area that needs to be considered, but as of this time, we do not have an active working group in PFAS.
Okay, thank you. Question for Dr. Ganaldi. Are there efforts to measure PFAS authorized by FDA to use in food packaging in the TDS samples? And if so, are there technical analytical hurdles that you're dealing with in that space?
So that is actually something that's going to fall under the work that we have, a new postdoc coming in that's going to look at some of those food packaging that's approved by the FDA. So that wouldn't be part of my work, but that is something the FDA is looking into in the future.
Okay, thank you. A question for Dr. Vorst. Can you give an example of total fluorine positive but not related to PFAS, and in which material? What are the levels of total fluorine found in recycled material?
Oh, that's an excellent question. So that has to do a lot with processed water. We see differences in recycled materials geographically, where they're coming from, where they're sourcing the pulp, what treatments have been applied to the pulp, if it's a molded fiber, if there's been a treatment in the mold as a release agent, and then a subsequent treatment. So these fibers get mixed back in the chemistries in the wet chemistry of the paper. So an example of a product, yes, absolutely. We tested a product not that long ago, right? I want to say everything seems like I put it in terms of pre-COVID now, so it would have been about January. We tested some molded fiber that had from the manufacturer no PFAS treatment, long or short chain, but yet we found significant levels of PFAS. And we also tested some products that were definitively contained a PFAS treatment, contained some fluorochemistry as a coating, and we did a total fluorine on it. It came back at I want to say right around 80 to 90 ppm. So by a lot of the numbers we're seeing pushed out, whether European or US at the 100 ppm threshold level seems to be a number people want to use. It would not have been identified as containing a PFAS treatment, but it absolutely did. And we worked with the manufacturer to identify what the treatment was after we tested it. But so yeah, we see that quite a bit.
Thanks, Dr. Vorst. There's a general question that all three of you can take a stab at. What is the path forward to get a standardized method, especially for sample prep, considering that regulations are going into effect already or very soon? What officiating body would be releasing standardized methodologies when they are out?
That's a great question, and we're just trying right now to identify so we work with several labs, several private labs, and we get some of their methods, and they're very different from lab to lab. So the first thing we need to do is start doing some cross-validation between labs on a couple different methods, and then look at what the recovery rates are and the repeatability of those methods. So my lab's doing a lot of that front-end work. We're trying to identify what method for particle reduction or size reduction works that yields us the highest recovery rates. It's not atypical for us to get a sample report from a private lab that says up to a 30% variability from the results report. We see that quite often. But as for a governing body that would look at that, I think there's different regulatory agencies that would be interested in that. I know the EPA has looked at some of that for landfill and some of the runoff sludge cleanup and some of the effluent cleanup. So there's an option there. But FDA, AOAC, and even ASTM, I think might even have a role.
Neil, EPA is currently working on a method for, I'll call it mixed matrices, so non-potable waters, solids, biosolids, tissue, apply to tissue. It'll be something along the lines of, and I think next year, hopefully, we're gonna see this, but it'll be along the lines of the same kind of methodology that's used for dioxins and furans or PCB congeners, which we oftentimes then adapt that to then apply to food matrices. So there will be something from EPA, but I think too, between ASTM and I'm waiting for Susie to jump in, FDA, that their expertise, especially with regard to food, that's really, that would carry great strength, I think.
Thank you. Any perspective from your end? Dr. Orlandi?
So one of the things I was going to at least point out, this is one instance, but in a number of other instances, usually the regulators will in a way, lead the way. If they are providing a method that they have developed that meets their regulatory needs, in the absence of any consensus, most laboratories will look towards the regulators, because it is those bodies that will ultimately look at the data, and they will be the ones using it in their surveillance. That being said, the greater consensus actually comes from standard development organizations, where they incorporate the needs of the regulators and the capabilities and requirement, the broad capabilities and requirements, and bring them together to develop and implement methods.
Thank you. Question for Charles. Have you looked at using NIST standard reference materials to validate the modifications that you are making to the PFAS, the EPA method?
Yeah, the issue we've had with the NIST standards have been a supply or consistent supply. Now it's been a little bit since I checked the catalog of what they had with regard to PFAS, but at an EMDQ meeting from last year, we had a specific report on NIST standards as it related to PFAS, because the DoD has a big interest. You know, a lot of what, and this is outside of the food realm, but a lot of what the DoD is responding to at military installations with regard to contamination from AFFF, they're reaching out to NIST for standard reference material to be used for comparison of the methods and sort of a normalization of the methods, exactly to the questioner's point. I do know there, Australia, the NMI, National Measurement Institute in Australia, they do have a program, but it's not, how do I want to say, it's not universally or regularly available to us in the States. I mean, we do have access to it, but it's just not as well known or as prevalent in the States.
Thank you. So general question for all of you. Do we know the residence time of PFAS in a paper mill after PFAS has stopped being used? Or
Yeah,
maybe
it's
this would
forever.
be-
You want to know the real answer? If it's in there, probably forever.
Yeah.
I've gotten processed water. I've gotten paper from mills that have not used according to them, not used a PFAS treatment for years, and we still get some pretty reasonable concentrations.
And if I can just add to that, this isn't specifically with paper mill, but other manufacturing processes like AFFF, you have manufacturers of AFFF that are going away from and manufacturing non-fluorine containing AFFF. We get asked to test those all the time and do the top assay on those, and we still find residual. So it's almost as if you would have to have a quote unquote virgin plant or facility before you could manufacture something that was PFAS free.
Thank you. It's another general question. This is about cooking material. What do we know about the risk of transfer of PFAS from cooking materials such as Teflon type coated pans into foods?
This is Susie. I can speak on that. We have done some work previously on that, and pretty much is what they found is after the first use, very little, migrates to the food. So there might be a little bit from the first use, but after that, they don't think it's really much of a concern.
So I'm going to ask a question from my perspective, Dr. Canaldi, which is when you overuse the pan and it gets to be sort of kind of charred and scrapey, does that increase the potential as far as you know for material? Or is it just on the very surface?
I'm not clear. I just, from what I understand, the analytes prefer to stay, in the polymer in the pan. They don't really have, much desire to, migrate out. But
Neil, if I could just add, I mean, at that point, it becomes one of the polymer form versus the non-polymeric form, and what to Susie's point, after the first use, what gets leached out is the non-polymeric form that was used in the processing of the polymeric form to actually make and create the coating. So, and actually sort of in sampling venues and in the lab, you know, the adage is old Teflon is probably good Teflon, because old Teflon, it's been exposed to solvents and washing and the like, and at some level you're reducing the amount of these anions, the surfactants that are used in the processing. They may still be there, very, very low levels, but at such low levels we're not able to detect them.
Okay, that's good to know. Thank you. Question for Dr. Orlandi. When is it expected to have AOSC methods to test PFAS in food contact materials?
I think it's relatively obvious. The need is to begin approaching standards development, and I think based on our timelines, within 6 months, a standard could be developed and a call for methods immediately after that, start to finish, perhaps 12 to 18 months.
Okay, thank you. Well, I think I've pretty much covered all the general categories that I've come across. If you have a burning question that you really would like to have answered the next minute or so, just type it quickly in the chat. I'm sorry, in the question. Actually, I just see one that have come that says the following: have you also already tested paper cupcake cases? And what have you found there?
Yeah, we've done that.
And what have you found?
I can't really. So we work for, I can just tell you folks, we work for a lot of brand owners. We do work for quick serve restaurants, not to refer to as fast food restaurants. And we've done that work. We've done it. I can't release it. It's private, but it's being addressed by the brand owners. Let's put it that way.
Okay. Very good. Well, I think with that, we will bring this session to a close. Thank you, everybody, for your attention. Thank you to all our presentations for wonderful and scintillating presentations. And just a reminder, we are recording the session, and all the registrants will receive an email with a link to our YouTube channel where you can view the presentations within the next few days. Dr. Jones, have any final comments? Might want to unmute.
Absolutely. Just to echo your comments there, Neil, thank you to everyone for joining us for the PFAS session today. Big thank you to all of our presenters, and I'll make a last minute reminder to folks still with us that we have recently launched the registration for our ILSI North America annual meeting, and hope to see many of you there as well. Again, thank you.
Yep, and stay tuned for the next sessions on migration and toxicology later on this summer. So thanks again, everybody, and have a good rest of your day.